Okay, here is this energy number 4. We have now at our disposal these equations, or mathematical models, call them sometimes. And this little warning here, be careful with units and unit conversions. Well, that's just to warn us that we need to make sure that when we have a K, a spring constant, that's got to be in newtons per meter. Whatever displacements we have, those need to be in meters, mass in kilograms, velocity meters per second, height in meters. So here, for example, right off the bat, how much kinetic energy does a 2,000 kilogram SUV traveling at 70 miles per hour have? Well, that's all fine. Here's my model for that, but I can't use that. I needed to change that to meters per second. So let's do that real quick. 70 miles per 1 hour. In 1 mile, there's about 1,600 meters. And in 1 hour, there's 3,600 seconds. So that's about 31 meters per second. And that means our kinetic energy is going to be 1/2 mass, needs to be in kilograms, so that is what we want right there. So that's about 961,000, and that unit for energy is joules. All right. How much energy does a 180 calorie half-pint carton of chocolate milk store? And 1 food calorie is about 4,186 joules. So, well, if we have 4,186 joules per calorie, and I've got 180 calories, then that's all we need to do there. And if you're thinking to yourself, wow, that's almost as much energy as that SUV. True, but the conversion of that energy into like the usable energy that your body would make out of it, there is very much inefficiency there and a lot of energy lost. Determine the gravitational energy of your 3 kilogram physics binder relative to the table it sits on in the classroom. And so this relative to, this means this is directing us to where we are going to pick the zero height. So for part A, I'm going to pick the zero height right there. So it's going to be 10 times mass times height. And in this case, that would be 30 times, 30 is the 10 times the mass, times 0, because it's at height 0. But what about relative to the floor? So relative to the floor means that I would make that the 0 height. So now times, if this is the 0 height, then the height of the book is the 0.68. That's about 20 joules. And then relative to the floor, that is relative to the floor, this should say the ceiling, sorry. So relative to this, if this is the 0 height, then what's the height of the binder? Well, the binder's below it, so that means it actually has a negative height. So that'd be negative 75 joules. How can something have negative energy, you ask? Well, with gravitational potential energy, the thing that's important for us when we start setting up LL diagrams and we have like a position A and a position B, it's the change in this quantity that matters, not what the actual number is. As you can see, depending on like what different reference point we pick, this binder can have 3 different values assigned to its gravitational potential energy. So it's a relative thing, and then what changes is what's important. So if we picked this, and then it went from here and it like fell to the floor, it would still have a change, like going from this negative number to even lower, and that change is what's important to us. So it's all good as long as you stick with your decision about what the zero height is. Number 4, bungee cord stretches 25 meters, has a spring constant of 140 newtons per meter. That is the correct units for us. How much energy is stored in the bungee? So elastic energy, 1/2 kx squared. I got my k, 140, with the right units. My x is in meters. That's the right units. So that's about, you can round that however you like. I'm just going to do 2 significant figures, round that to 44,000 joules. How fast does a 50-gram, that's wrong units, need to travel to have 40 joules of kinetic energy? So I know that my EK is 1/2 mv squared. This mass, 50 grams in kilograms, would be 0.05 kilograms. So if I want to have 40 joules of kinetic energy, 1/2 times the mass times the velocity squared. Need to do a little bit of algebra there. Oops, what did I do? Just need to take the square root of that, right? We were solving for the v there, so it'd have to be going 40 meters per second to have that much energy. How much energy is stored when a railroad car's spring is compressed 10 centimeters? Okay, so 10 centimeters. There's 2 ways we could do this. We can convert this to meters and this to newtons per meter, or we can recognize that if energy is equal to 1. No, just kidding. We need to convert them. So I need to convert this. 10 centimeters is 0.10 meters, and 10,000 newtons per 3 centimeters would be the same as, so let's write out the conversion to make sure we do it right. So I don't want centimeters, I do want meters. So that's wrong. That would be 100 centimeters is the same as a meter. So that would be 1,000,000 newtons per meter, per 3 meters. And I could also divide by the 3. So that's going to be 330,000 newtons per meter, rounded to 2 significant digits. Okay, so then I need to do that. 1/2 k x squared. So that's about 1,700 joules or so. All right. Now into the real stuff here. So a cart moving at 5 meters per second collides with a spring. At the instant the cart is motionless, what is the largest amount that the spring could be compressed? So trying to find here, what's that x? And assume that there's no friction, so we don't have any dissipated energy. I'll get rid of that. Define the system with the energy flow diagram. That's what we call an LOL diagram. Then complete the energy bar graphs qualitatively. Okay, so let's see what we can do. What's in the system? We've got a cart. We could put the entire Earth in there. It doesn't really matter if you put it in this case because we have no height change, so we don't have to worry about EG. I'll get rid of those. And we've got the spring. You could put the track in there. There's no friction, so it doesn't really matter if you put the track in or not. The things we really need are the cart and the spring, because this cart has kinetic energy, and then the spring takes up that energy over here, and the cart comes to rest. So the qualitative equation would just be EK is equal to EE. The quantitative version would be, well, now we know that EK is 1/2 mv squared equals EE is 1/2 kx squared. So I can actually go ahead and put numbers in now. That's the mass of the cart. You need to put those numbers in carefully. Okay, and you can do this all with your calculator. There's a lot of canceling out that can happen. I think that x is going to be 2 after you do the algebra. This 1/2 times 50 could have canceled that for, yeah, that's going to be 2 meters. Got to be a big spring. All right, that's how you do it. Number 8, rock is shot straight up into the air, and since this is the lowest point, that's going to be our 0 height. And this mass, 500 grams, that's the wrong units. That is 1/2 kilogram. That's the right units, and that's the right units. Okay, so I got my rock, the slingshot, the entire Earth. Those are the things I need in the system. So here it does not have any EG yet, and doesn't have any EK yet, so all elastic energy stored in that slingshot. And then here up at the top, it doesn't have any EK because it's reached its highest point and the velocity is 0. But it definitely has gained some height. Right? And assume no air resistance. That means that we're ignoring dissipated energy. So what's our qualitative equation would be EE is equal to EG. And then EE is 1/2 kx squared, EG is 10 mh. And we're trying to figure out the height that it reaches. All right, that's my K. That's how much it got stretched, the delta X. This is 10 times, that's the mass of the rock. And I'm going to figure out the height from there. I got about 90 centimeters or 0.90 meters. Number 9, determine the final velocity of the roller coaster assuming a 10% loss to friction. So we do have dissipated energy. It's 10% of the whole thing. So see if we can figure that out. So here I've got some gravitational potential energy. So up at the top of this hill. No kinetic energy. There's no springs in this problem, so no EE. And then at the bottom of the hill, I've got a bunch of velocity, but you know what? I'm going to make that 5 blocks high because then 10% would be half a block, right? So that's like almost as tall as this, but not quite, right? Should have done my system first. Let's do that now. So the Earth, the cart, and the track I'm going to put in there since we do have that energy lost. So my qualitative equation, this one's a little bit tricky. Oh, sorry, I put this stack in the wrong place. All right, let's leave it there, actually. I'll just do this, EK, right? And EG is equal to EK. How do we figure out how to do this, what that E dis is equal to? Well, there's a couple ways you could do that. I think the easiest way, if this is 10%, what is it 10% of? It's 10% of what we started with here, right? So it's 10% of the EG that was here. And then doing a little algebra, if this is like a whole EG here and we subtracted that, that would be this, which should make sense. We're going to end up with 90% of the energy is going to turn into the kinetic energy because that's how much was lost there. So hopefully that makes sense to you. So that's 0.9 times 10 times mass times h is equal to the 1/2 mv squared. And math is happening now. You might wonder, you might think that you're in trouble here, that you don't know the mass of the cart. Uh-oh. But look, it shows up on both sides, so it doesn't matter what the mass of the cart is. It cancels out. And then if I multiply both sides by 2, 100.9 is 90. So I'm thinking we got the square root of 90 here, so about 9.5 meters per second. There you go. And the last one. Moon could be an ideal spaceport for exploring the solar system. Moon launching system could consist of a magnetic rail gun that shoots an item into moon orbit. How much energy would be needed from the railgun to get a 10,000 kilogram capsule into an orbit that's 100 kilometers above the surface of the moon? The moon's gravitational field strength is this, and the orbital velocity is that. Okay, so that sounds complicated. Let's just go through and see if we can figure out what we're doing here. I'm going to make a little picture here. There's our railgun. So we're going to shoot this thing from here. And since that's the lowest it's at, we'll make that the height 0. And I'm going to shoot it up into orbit where it's got this height 1,000 kilometers. That's the wrong units for us. And it's going to have a velocity of 1,700 meters per second. So where is the energy here? I mean, we got to have the energy stored in the railgun. So you want to call that elastic energy? It's not exactly. How about if we just modify this and say energy of the railgun? So it's not exactly like a spring, sort of, kind of. So there's all that energy there. And here we've got a bunch of gravitational potential energy, and we've got a bunch of kinetic energy of its orbit, and we're not doing that. The other way you could do this would be to say, you know what, I'm going to put the railgun, did this say put it outside the system? It didn't specify for us. Oh, yes it did. So we won't do that. Instead, we will do railgun is going to do work. My little arrow putting, that's the work done by the railgun. Yeah, let's do it like that. It doesn't change anything if you put the railgun inside the system, inside the energy of the railgun. That's fine, either way. So if the railgun's outside the system, we do not put it in here. We just put the moon and the capsule. All right, so I think we can write our equation then. So this, the work done by the railgun, is equal to EK plus EG. And we're trying to figure out how much energy, so we're trying to solve for that. So EK, 1/2 the mass of the capsule times its velocity squared, plus, instead of 10 times m times, the 10 is not 10 on the moon, it's 1.6. So that's a little tricky thing you got to remember to do there. Gravitational potential energy on the moon is 1.6 mH, right? 10 is our local number for our gravitational field strength. So I got 1.6 times 100 kilometers is 100,000 meters. Oops, I'm getting the M and the H backwards. And then the mass of it is 10,000 kilograms. So if you're trying to match this up to the 1.6 mH, I put those in the wrong order. But of course, it's just multiplication, so that's okay. So let's crank that all out of the calculator. 1/2 times 10,000 times 1,700 squared plus 1.6 times 100,000 times 10,000. So that's about 1.6 times 10 to the 10th joules, which is about 16 billion. A lot of energy. All right, there you go.